In our hyper-connected world, we kind of take time for granted, right? It's just there. But for the massive computer networks that run pretty much everything, time is a total mess. There's no single universal clock they can all look at. So how in the world do they agree on what happened first? That's the puzzle we're going to untangle today.
Okay, so imagine this. You're trying to set up a meeting, but everybody's watch is different. Some are fast, some are slow, some are just weird. And there's no master clock on the wall to sync up with. How would you ever figure out who showed up first? How could you possibly agree on the order of anything? Well, for the huge distributed systems that power your bank, your social media feeds, everything, this isn't some hypothetical problem. It's their reality every single day. We're talking about maybe thousands of computers, each with its own little internal ticker, and absolutely no single source of truth for time. And that right there brings us to the real heart of the issue. The goal isn't really about knowing the exact time like on a wall clock. It's about understanding something much more fundamental: causality. Did this thing, A, actually cause this other thing, B? Just figuring out what happened before what. Getting that right is literally the only way these systems can work without falling apart.
All right, so let's dig into this. What exactly makes telling time so incredibly hard for these systems? Let's break down this problem of order. See, the engineers who build these things are up against some major hurdles. The computers don't have any shared memory they can all check. Their only way to talk to each other is by sending messages back and forth. And here's the kicker: you can't predict how long those messages will take to arrive. So with no global clock, using physical time to figure out the real order of events becomes, well, basically useless. So how do you even begin to solve this? Well, the first big aha moment came from the brilliant computer scientist Leslie Lamport. He had this amazing insight. He said, let's just ignore physical time completely. We just need a logical way to put events in order. His idea was just so elegant and simple. He said, let's just count. So instead of all the messy business of seconds and milliseconds, each computer or process just keeps track of a single number. That's it, a simple integer. This number becomes its logical clock. It starts at 0 and just goes up. And the real magic here is in two incredibly simple rules. Rule number 1, super simple. If a computer does something on its own, it just ticks its own counter up by 1. Done. But rule number 2, this is the clever part. When it gets a message from another computer, it looks at its own clock and the timestamp on the message. It sets its clock to whatever is higher, and then it ticks up by 1. This is how the system kind of learns from the past and forces itself to respect the flow of cause and effect. And what you get from this is a really important guarantee. If event A genuinely caused event B, like A sent a message and B is the reply, then A's timestamp will always be smaller than B's. Causality is preserved. It looks like we've solved it, right? Seems to work perfectly. But is that the whole story? Yeah. It turns out that this simple counter, as clever as it is, has this tiny but absolutely critical flaw. It tells us the truth, but maybe not the whole truth. And here's where it gets tricky. Look at this. Two events on totally different computers that have nothing to do with each other can, just by coincidence, get the exact same timestamp. And maybe even worse, you can have one event with a timestamp of 2 and another with a timestamp of 4, making it look like one caused the other when in reality they're completely unrelated. So these simple scalar clocks, they can create this illusion of a connection where there's really nothing there at all. And this really gets to the heart of the problem. We know for a fact that if A caused B, its timestamp will be smaller. But does it work the other way around? If you see that timestamp A is smaller than timestamp B, can you say for sure that A caused B? And the answer, unfortunately, is a big nope. Not necessarily. That smaller timestamp could just be a total coincidence. The two events might be completely independent. What's happening is that scalar time is giving us false positives. It can't tell the difference between true cause and effect and just random chance. So let's just nail this down. With a simple scalar clock, seeing that A's timestamp is smaller than B's only tells you that A might have happened before B. You just can't be sure if they're actually connected. And for building the systems that we all rely on, might just doesn't cut it. We need to know. We need a clock that gives us definitive answers. So to get that kind of certainty, we need a serious upgrade. We need to move on from that single, lonely number to something much, much more powerful. It's called a vector clock. And this is how we get the full picture.
This is such a cool idea. Instead of just one number, each computer now keeps a whole list of numbers, a vector. So let's say you have 3 computers in your system. Now each one keeps a list of 3 numbers. The first number is its own clock, and the other 2 spots in the list are for tracking the latest times it has heard from the other 2 computers. It's not just aware of itself anymore, it's aware of what it knows about everyone else.
The rules get a little upgrade too, but they're still pretty intuitive. For a local event, you just increment your own spot in the vector. Easy. But when you get a message, you first merge your vector with the one from the message. You go down the list, element by element, and for each spot, you take the higher number. And only then do you tick up your own spot in the list. It's this constant merging of knowledge that builds up a super rich, accurate history of what really happened.
Now, this leads to a pretty fancy-sounding word you see here, isomorphism. But the idea behind it is incredibly powerful. It basically means that with vector clocks, there's a perfect one-to-one mapping between the timestamps and the actual real-life causal history of events. So now, if you see that timestamp A is less than timestamp B, you know for a fact that A caused B. All that guesswork, it's gone. We have proof.
Okay, so great. We found the perfect clock. Problem solved, right? Well, in the world of engineering, there is never, ever a free lunch. All of this incredible power comes at a price, and that leads us to a classic trade-off. And this table here really lays it all out. You've got your scalar clocks on one end. They're dead simple, super light, but they can't give you that perfect causal picture. Then you've got vector clocks. They give you that perfect picture, but now you're sending a whole list of numbers with every single message. If you have thousands of computers, that list gets really long. And that's a lot of extra data to send around. And yeah, there are even more powerful things like matrix clocks, but the overhead on those is just massive. Okay, I know what you might be thinking. This all sounds super abstract, right? Just a bunch of theory. But believe me, the choice between these different kinds of clocks has huge, real-world consequences for the technology we all depend on. This is not just some academic puzzle. Logical clocks, whether they're the simple ones or the more complex ones, are the unsung heroes, the invisible engine running quietly in the background of our digital lives. They're what keeps things from descending into chaos. And you see their fingerprints everywhere once you know where to look. They're what keeps distributed databases consistent, making sure your bank balance is correct, no matter which computer you happen to connect to. They're critical for tracking down bugs, for recovering when things crash, and for making sure everyone gets a fair turn when they all try to access the same thing at once. So, after this whole journey, from a simple counter to a complex vector, it really all boils down to one fundamental question. In this messy, distributed world we've built, how much are we willing to pay for certainty? How much complexity and overhead are we willing to accept in exchange for a perfect memory of the past? The answer to that question defines the invisible systems we rely on every single day. Thanks for joining us on The Explainer.